isomers of alkene or conformational isomerism. So, what is conformational isomerism? Conformational isomerism is a form of stereoisomer in which the isomer can be interconverted exclusively by rotation about the formerly single bond. Okay, so it's free rotation across the carbon-carbon chain. That means the conformation, the two compounds will interchange between the free rotation across the single bond. Such isomers are generally referred as conformational isomers or conformers, and especially known as rotamers. So what is conformational isomerism? It's a form of stereoisomerism in which the isomers can be interconverted exclusively from by rotation about the formerly singly bond. Okay, so across the single bond, due to the free rotation, these isomers are formed. Okay, so why should we study this? Why should we study this? Okay, what is the use to study this? The study of the energetics between different rotamers is referred to as conformational analysis. So what are the energies which is associated with different forms of these rotamers or constitutional isomers can be studied, and this is known as conformational analysis. And it is useful to understand the stability of different isomers. It is used to understand the stability of different isomers. In addition, conformational analysis can be used to predict and explain the product selectivity, mechanism, and rate of reaction. So which conformation will be more stable, which will be more favored. So this can be understood by the study of conformational analysis. So this is the basic thing that we have to know. Now, types of conformational isomers. The type of are related to the spatial orientation of the substitution between the two vicinal atoms. So what is two means? Adjacent. Vicinal means adjacent. So conformational isomers is related to the spatial orientation of the substituents or between the two vicinal atoms. Okay, these are of two types, eclipsed and staggered. There are intermediate different Gauss conformation, but the major one which we are studying is your eclipsed and staggered configuration. Okay, the staggered configuration includes Gauss, that is plus or minus 60, anti, that is 180 conformation, depending upon the spatial arrangement between the two substituents. Okay, so what is now eclipsed? Now what is now eclipse? In chemistry, an eclipse conformation is a conformation in which two substitutions are at the close proximity. When the two substituents on the adjacent carbons are at the close proximity, then it is said to be eclipsed. So in organic chemistry, a staggered configuration is a chemical conformation in which the substitutions are at maximum distance from each other. This requires a torsional angle of 60 degrees. So there should be 60 degrees angle between the two substitution, minimum 60 degree angle between the two substitutions. This is staggered configuration and eclipsed. So you have to know what is staggered and eclipsed. When the two conformations substituents are the closest proximity, they are just one behind another, then it is said to be eclipsed. When they are, it is a maximum distance between the two substituents at the adjacent carbon with the minimum angle of 60 degree, then it is said to be a staggered configuration. Now let us go for the conformations or analysis of ethene. That's the first compound, that is ethene. So ethane is what? C2H6. Okay, there are two carbons. Each carbon has got 3 hydrogens attached to it. So when you take it in a Sawhorse conformation, you have got 2 carbons with 3 hydrogens. Okay, this is your, and when you see in Newman's projection formula, there will be 2 carbons, one ahead and one behind. Okay, there will be two configuration. The barrier of rotation of two methyl groups in ethane is approximately 2.9 kilocalories. So from one conformation to another conformation, they require an approximately 2.9 calories kilocalories per mole of your energy to go from one conformation to another. And since this amount of energy is readily available in room temperature from due to molecular collision, the methyl group is said to have a free rotation. So the methyl groups in ethane, because of this low energy required for your rotation, so they are always said to be in free rotation. The rotation motion within the ethane can be represented by the dashed or the wedge notation. So this is the wedge diagram where we can see three hydrogens. So when they rotate, your hydrogen goes down. So there are the three conformations that you can see. During rotation, the conformation moves from staggered to eclipsed. It moves from the staggered to eclipsed to a second staggered conformation. So this is the rotation. Now let us go for the next one. So what is staggered? So let us see in a Saur's formation. If you see a staggered configuration, if you see the two hydrogens on the adjacent carbons, they are minimum at that angle. They are separated by a 60-degree angle. They are not one behind another. Okay. Whereas when you see the eclipse, the two hydrogens of your ethane, okay, they overlap each other exactly behind each other. So the dihedral angle in case of your eclipse conformation is 0, whereas in case of staggered configuration, the dihedral angle is 60 degrees. So these are the two conformation, eclipsed and staggered conformation of your ethane. So now let's see the conformational analysis of your ethane molecule according to the dihedral angle. So the barrier of rotation in ethane is about 2.9 to 3 kilocalories per mole. Okay. Now let us see the first conformation. What is eclipsed? The first conformation is eclipsed, which is how much degree? It is 3.0 kilocalories away from the staggered conformation. So it is, if you see, the first one is your eclipsed when both the hydrogens are, if you see, you have to look at the hydrogen which is red in color. So when we move, what happens? Now when we move around 60 degrees, when we move the group in a clockwise direction to a 60 degree, you get a staggered configuration. And in the staggered configuration, the energy is, it's the most stable one, so it is 0. Next is another eclipse conformation. When you move by 120 degree, the two hydrogens again come close to each other. Okay, you read, if you see, the hydrogens come close to each other, that is the eclipse conformation. Again, it is unstable. They got around 3 calories more from your staggered configuration. Again, when you go for 180 degree, the hydrogens go apart. You get a stable staggered configuration. Again, when you go by 240, again you get the eclipse configuration. You have to see by the rotation. So you have to always show your color of one of the hydrogen by a different one, so that you can come to know how the staggered configuration in case of methyl, in case of hydrogen. So this is how 300-degree rotation. Then you are again, it is a staggered, and again when you view a 360 degrees, comes to a 360, it comes back to its original position. That is your eclipse configuration. So this is the conformational analysis of your butane. So you should draw all this structure. And in this case, when the angle is 0, 120, 240 and 360, the two hydrogens adjacent carbons are said to be in eclipse conformation, and when they are in 60, 180, 300, then the compound is said to be in staggered or the most stable. So these are the dihedral angles in which the ethane molecule will be in your staggered as well as in your eclipsed conformation. Now let's go for the next conformations of propane and butane. So let us go one by one. These are the two, propane, and this is the Newman's projection formula for your propane and butane. So let's go one by one. Now let's start with propane. So when you have propane, front carbon has 3 hydrogens, if you see, and the back second carbon from behind has 2 methyl and 2 hydrogens and 1 methyl substitute on the carbon. On the second carbon, there will be 2 hydrogens and 1 methyl. So this is how it will be seen. So when you convert it into a Newman's projection, the front carbon you can see with the dot and 3 projection outside, it is hydrogen. And the back carbon, look at the back carbon. You have got 1 methyl and 2 hydrogens and 2 hydrogens. So in this is how the projection formula for your propane. So now let us go for each conformations. Now let us go for each conformations of your propane. So what is the eclipsed? When methyl and your hydrogen are close to each other, then it is said to be your eclipsed conformation. Now rotate your hydrogens and you see what happens. When the dihedral angle is 60 degree, it is the most stable conformation, that is your staggered conformation. That is your staggered conformation. So what's the torsional? So what is the distance between your eclipsed between hydrogen and your methyl? It is 1.9 angstrom. Whereas in case of staggered, the distance between your hydrogen and your methyl is said to be 2.48 angstrom. That means they are far apart from here, and that's why there is less torsional strain. That is mutual repulsion between your adjacent carbon. Okay, this is known as torsional strain. So eclipsed is when there is 0 methyl and H. You have to draw the different conformation. So when you remove it by 60 degrees, your hydrogen comes away. So that is your stable conformation. Again at 120, your 2 hydrogens will come. Okay, and it comes next to your 1 methyl. Okay, so this is how the conformation. So when the methyl and the hydrogens are close to each other in the conformation, it is said to be an eclipsed conformation. And when hydrogens and hydrogens are close to each other, it is said to be an eclipsed conformation. And when they are apart from each other with the bond angle of dihedral angle of 60 degree, then it is said to be a staggered configuration. And we have to show this diagram. Okay, this diagram has to be shown. This graph has to be shown in your. Okay, so please mention this diagram whenever you show the diagram. Okay, now comes your butane. Now comes your butane. So what does this butane contains? If you see the butane structure, the carbon second and the carbon third, which will be viewing. So which carbons will be viewing in butane? There is 4 carbons, but we will be viewing the second and the third carbon as a central carbon. Okay, the second carbon contains 2 hydrogen and 1 methyl. Third carbon also contains 2 hydrogens and 1 methyl. And when you view it, okay, when you view it, so you have got methyl, hydrogen, hydrogen, methyl. So this is an eclipsed conformation. Okay, and this is what is the partially eclipsed? When the methyl and H are close to each other. Okay, so these are the various conformation. And gauche conformation, when methyl and methyl are away from 60 degree, that is your gauche conformation. So these are some of the possible structures of your butane. So you have to see, we have to focus on which carbon? It is the second and the third carbon of your butane, which you have to see in your Sawhorse formation, and just convert it into your eclipsed form. Convert to your eclipsed form, and then if you rotate it by 60 degree, you get your gauche or your form, and the most stable form is your anti. So these are the possible conformations of your N butane. Now let's go one by one. So what is your gauche interaction, or This is a type of, this is a type. See what conformation in, because in this case there is an extra interaction between methyl and H. Okay, so when there is a degree dihedral angle degree of 60 and 300, so when you rotate your molecule, when you rotate your butane molecule, two carbons of your butane, so when it comes to 60 and 300, when the dihedral angle is 60 and 300, okay, when the dihedral angle is 60 and 300, when you rotate the molecule, when the dihedral angle comes to 60 and 300, the conformation is said to be, Gauss conformation. So what is this Gauss conformation? In this case, the methyl groups are having a 60-degree deviation from the another methyl group, okay, from your another methyl. So this is your Gauss conformation. This is your Gauss conformation. They have got slight repulsion of +9. So remember, because of the close proximity to your methyl group and the hydrogen, they have got slight repulsion force. So they have got an energy of 0.9 kilocalories. So they will not be zero. There will be some repulsive interaction. Okay, and that is of 0.9 kilocalories. And the most stable and the lowest conformation of your butane is when the two methyl groups are at opposite end, or it is known as anti-conformation. It is known as anti-conformation, or the most stable staggered conformation. Most stable conformation. Okay, the methyl groups are anti-periplanar, means they are exactly at the opposite sides to each other. So that is the most stable. That is known as your Gauss conformation. Even through the two adjacent carbons are staggered, there is a small repulsion between the two methyl groups when they are separated by 60. As I said, there will be a torsional strain in the molecule because of their close proximity. Okay, and these are known as Gauss interaction. Okay, and the Gauss costs about 0.9 kilocalorie relative to your staggered conformation, as the two methyl groups are antiplanar to periplanar to each other. So the most stable configuration is the one that you see on the right, that is known as anti-conformation, and those on the left are known as Gauss conformation. And you got the most stable conformation when the dihedral angle is 180 degrees. Okay, please remember this. Now comes the eclipsed. Now what is eclipsed? Okay, now what is eclipsed? You see from the second and the third, the two methyl groups are next to each other, that is known as the fully eclipsed conformation. That is known as fully eclipsed conformation, where both the methyl groups are on syn. That is, your dihedral angle is 0. And the two methyl groups are on the same side. Okay, syn, that is on the same side. Then it is known as fully eclipsed with the back carbon. Okay, or the front. Two methyl groups of front and back are said to be fully eclipsed, and they have got the highest energy conformation of your butane. Okay, the strain energy is about 5 kilocalories above the staggered configuration at the right. That is the most stable configuration. That is the anti-configuration. They have got an strain of more than this particular eclipse conformation, that where both the methyl group are synced to each other. Then it is the conformation is the fully eclipsed. They have got the maximum energy. When methyl and H, they have got slightly lesser energy compared to that of your methyl and methyl. So this is known as fully eclipsed structure, and the strain energy is around 5 kilocalories above the staggered configuration. That is your anti-configuration. So remember this thing. Now there are two more eclipse conformation. Why there are two more? As I said, the methyl and H, and there are two methyl and methyl and H. There are two more. So when the dihedral angle is around 120 and 240, when the dihedral angle is around 120 and 240, the methyl and H comes close to each other. There are two methyl H eclipsing interaction, each having an energy of 1.4 kilocalories, and between one hydrogen and hydrogen, the eclipsing interaction is your 1 kilocalorie. So total there will be in this case the bond the steric energy associated is 3.8 kilocalories. 1.4 1.4 of your methyl H and 1 of hydrogen. So there will be total energy of 3.8 kilocalories. 3.8 kilocalories. So understood why there is a change, because there is no methyl interaction in case of here this two when the dihedral angle is 120 and 240. This has to be remembered when you draw the energy analysis. So this is what happens, conformational changes that occurs between your two methyl groups. That occurs between the two methyl groups. So the first is when first conformation is your fully eclipsed. The first conformation is your fully eclipsed structure, okay, where the dihedral angle is 0. That is your fully the most unstable or high energy structure, that is syn eclipsed. Okay, dihedral angle is 0. Now when you move by 60 degree, that is your Gauss staggered. That is your Gauss staggered conformation, where your methyl and methyl are apart from each other by an bond dihedral angle of 60 degree. Now further 60 means 60 plus 60, 120. In this case, it is eclipsed, partially eclipsed, because there is methyl and H interaction. There are two methyl and H interaction. Okay, when the bond angle is 120, dihedral angle is 120. That is your eclipse. Now the most stable configuration is attained when the dihedral angle is 180. So if you see in this structure, the two methyl groups are exactly opposite, anti to each other. So they are far apart from each other. There is the least interaction, and this is said to be the most stable conformation of your butane. This is said to be the most stable conformation of butane. Then you go to your another, when you still rotate it by 240, you still rotate it by 60, you get your dihedral angle of 240. Again, you got a eclipsed conformation. You get an semi-eclipsed conformation with your strain energy of 3.8 kilocalories, because there is a methyl and H interaction. No methyl interaction. There is a methyl and H interaction. Now goes to your Gauss. So again, when you go to 300, you get into a Gauss conformation, and then you go. They have got slightly more energy because of the slight interaction, 0.9 kilocalories, because of the methyl and hydrogen interaction, because of the close property of methyl and hydrogen. So they got an these are, and the next one is your, then again you go to 60 degrees, and when you come to 360 degrees, again you come to your fully syn eclipsed conformation. That entire rotation takes place, and again you come back to your syn eclipse conformation, that is the high energy conformation. So these are all the conformers of your butane. These are all the conformers of your butane. Now let's go and look into the energy. So that is, if you see the first structure, that is syn periplanar, where the methyl groups are close to each other, highest energy, okay, that is 5 kilocalories. Next is your Gauss conformation, where your methyl and methyl are at close proximity, okay. So they have got 0.88 kilocalories more than your most stable anti-periplanar current. Again they go to into your eclipsed, but in this case the energy is 3.6. The energy is 3.6, whereas in case of syn periplanar the energy is 5 kilocalories, okay, which is less than your syn periplanar conformation. Then again it goes to the anti-periplanar, the most stable, where the energy is 0. Again it goes to your eclipsed, that is partially eclipsed conformation, okay. Then again it goes to your Gauss conformation, and again then it comes back, when it comes to 360 you get a syn periplanar conformation, and your energy associated is 5 kilocalories. So these are the various energy levels which are associated with your conformational isomers with your butane, with your conformational isomers of your butane. Okay, so this is what you have to know about your alkanes. Okay, so the next part is your stereochemistry of alicyclic compound. Stereochemistry of alicyclic. What are alicyclic compounds? What do you mean by ali? That is aliphatic cyclic compound. Means they are saturated cyclic compounds. So alicyclic compound means the compounds which are cyclic and which are saturated. Okay, they are known as alicyclic. Like the examples are cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane. All of these are said to be alicyclic. They are cyclic and saturated ring. Okay, there is no unsaturation. So they are known as alicyclic compounds. Now these compounds also show your stereochemistry. In case of your carbon-carbon single bond, there is free rotation. So they always form a conformational isomers. Okay, because of the free rotation. Can you rotate your cyclic compounds, alicyclic compounds easily? If you want to rotate, you have to break the bond. So there is something called restricted rotation. And whenever there is a restricted rotation in your compound, in an enantiomer, they are said to be geometric isomers. Okay, they are said to be geometric because of the restricted rotation across the carbon-carbon single bond. If you try to rotate it, it will break. It will break. So such type of compounds where there is a restricted rotation carbon-carbon bond, they exhibit geometric isomers. Along with this, they show your optical isomerism. Also, okay, they show optical isomerism. So there are cis and trans. So when the two methyl groups, okay, let us say an example of 1,2-dimethyl cyclohexane. So if you see the one which is shown in a darker boundary, it is known towards us, and which is shown with a lighter one, it is away from us. The one which is shown above is above the plane of the vertical line, and one is shown below, it is known as below the plane. When the two groups are on the same side, then it is said to be of cis conformation, and when it is on the opposite side, the plane, it is said to be trans isomers. So this is, thus they show isomerism. But why they are called? Why they are called geometric isomerism compound? Because of the restricted rotation across the carbon-carbon sigma bond. If you try to rotate the sigma bond, your entirely molecule breaks open. The molecule breaks open, and this exhibits a geometric isomerism due to your restricted isomerism. Now let's go for the next. As you said, cis and trans, because the ring does not rotate freely in the space like linear chain, two different possibilities exist. As I said, cis and trans. When the two groups are on the same side, it is known as cis, same plane, and when they are on the opposite plane across the two rings, then on the different sides of the ring, then it is known as trans isomers. Now let us see, can they show optical isomerism? Can they be chiral or can they rotate the plane polarized line? Let us see that. Geometric isomerism seen, whether they show optical isomerism. How they show optical isomerism? Let us see the example of cis and trans cyclic compound. Okay, let us take 1,2-dichlorocyclopentane. Okay, it's achiral. Why it is achiral? So they are first of all, they are superimposable on their mirror images. That is the first intent. Moreover, they contain what? Moreover, they contain a internal plane of symmetry. They contain what? They contain internal plane of symmetry. So this is one of the element of symmetry, since they contain internal plane of symmetry, because both the groups are, when you draw a line in between two groups, it has equal, so they are superimposable on each other. So this is known as internal plane of symmetry. That's why they are said to be achiral. Now let us take the example of trans 1,2-dichlorocyclopentene. They are said to be chiral. So one chloro is H, one chloro is down, and they form a non-superimposable mirror image. If you see, they cannot be superimposed. So such type of compounds are said to exhibit your optical isomerism. They exist as enantiomers. So the trans isomers usually show your optical isomerism because they exist as an pair of enantiomers. So trans isomers are said to be enantiomer because they form non-superimposable mirror image of each other, and if you see, there is no plane of symmetry. One chloro is up, other chloro is down. So there is no plane of symmetry, internal plane of symmetry. That's why this compound, trans compounds, isomers show optical isomerism, or they exhibit your optical activity. They represent a pair of enantiomers. They may rotate the plane of plane polarized light. So that's why your trans isomers in case of cyclic compounds show optical isomerism. It shows both your geometric isomerism as well as optical isomerism, because geometric isomer because of the restricted rotation, and optical isomer because the two groups are on the opposite side and they do not form a they form a non-superimposable mirror image of each other. That's why they are said to be your optical. And if you take cis and trans, they are said to be diastereomers. Cis and trans isomers are said to be diastereomers. They are said to be because they are non-mirror images of each other. So this is how you can explain isomerism in case of cyclic alicyclic compounds. Okay. So let's go by one. Now let's go for your conformation of cyclohexane. Okay, cyclohexane, yeah, if you see, as we have studied, it is free to rotate. It is free to rotate with a tetrahedral angle of 109, which is the most stable structure for your sp3 hybridized carbon. Okay, so they can rotate easily and adopt three-dimensional structural conformation of boat and chair. So they can go into your boat as well as chair. So this is your chair, this is your boat. Okay. Now, what are these chair? There are totally two chair conformations which are said to be the most stable, and one boat conformation. So there will be a transformation from one chair conformation to other chair conformation, and in between there will be an intermediate stable conformation of your boat. It will be in between the two chair conformation, there will be one boat conformation. Okay, if you look closely, we'll see that if the red carbon bends, you will have the boat, and if the blue carbon bends down, then you get the second chair conformation. So there is a change when you try to rotate the bonds between the carbon single bond. There is a change in conformation. One boat chair conformation gets converted. One at the first position, here the red one is down and it goes up. Okay, so this is the change that happens. That's why it is said to be a conformational isomer. If you see it over here, you flip your boat, you get these are the different types of boat formation, and these are the intermediates which are present when you flip the structures, when you flip the boat to get into your another chair conformation. So now cyclohexane bonding stability. What is the steric strain occurs between the substitution either both axial or axial have high energy, or equatorial which has low energy. The mono-substituted cyclones are more stable when they are equatorial. So any substitution which is there, the most favored conformation is when the substituent is always equatorial. They have got low energy. Okay, they got lowest energy. Always places the largest group. That's why all the groups, large groups, should be placed in a equatorial conformation. So now, how to draw a cyclohexane? How to draw a cyclohexane molecule? So first we have to draw two parallel line. First we have to draw two parallel lines. If you see, first draw two parallel lines. Okay, slanting downwards. Okay, slightly offset off from each other. This means that the four cyclohexane carbons lie in the plane. They lie in the plane. Okay, the four carbons which are parallel, they lie in the plane. Place the topmost carbon above to the right of the plane of the other four. So you have to take at the right top one at the top and then connect both the bonds. If you see at the right hand side, one carbon is just slightly above. Okay, and you have to connect. Now go to the left hand side, bottommost carbon. Okay, and to the left of the plane of the middle four and connect. So draw a one. So this is how you try to form a cyclohexane. Note the bonds to the bottommost carbon are parallel to the topmost. But if you see this one, if you see the cursor, so these two are also parallel. These two bonds between the bottommost and the topmost. These two bonds are also parallel to each other. So this is how you draw a cyclohexane molecule. This is how you draw the cyclohexane molecule. And these are the various conformations. This is when you try to shift it. First it goes to an half chair conformation, then it goes to a twisted, goes to boat, again to the twisted boat, half chair conformation, again you get the chair. So there are 1, 2, 3, 4, 5, 6, 7 conformers of your cyclohexane. It goes to 7 conformers before it changes from one conformation to another chair conformation. Now, how to draw the axial and equatorial hydrogen? So now what do you mean by axial bonds? What do you mean by axial bonds? There are total 6 axial bonds in your cyclohexane because there are 6 carbons, so there will be 6 axial bonds. Okay, they are all parallel and upwards and down. They will always perpendicular to the plane of the bond, their carbon. So these bonds at the top or bottom, they will be perpendicular to the plane of the carbon. So if there is a carbon, if your carbon 6 carbons are there, and these hydrogens will, the substituents which are axial, will be always perpendicular to the plane of your carbon plane. Okay, there will be alternate up and down. One will be up, other will be down. One will be up, other will be down. Now the equatorial bond. So there will be 6 equatorial bonds, one on each carbon. There are 3 sets which are parallel to each other. So if you see the structures, they are along the plane. Okay, they are along the plane of your carbons. Means they are along the plane. So you can see 2, 2. They are along the plane. And when you completed structures, one top, one will be perpendicular, one will be along, one will be perpendicular. So if you say alternate, one axial bond is top, other will be other will be on the bottom of the. Similarly, if you see, this is the complete structure of your cyclohexane. This will be the complete structure of your cyclohexane. This is the complete structure of your cyclohexane. 6 axial bonds which are perpendicular to the plane, 6 equatorial bonds which are along the plane, and the axial bonds are alternative, top and bottom, top and bottom. So this is how you have to draw the cyclohexane. So now why that flipping occurs? So if you see the structure, you see only at the axial bonds. When you rotate the axial bonds, when you rotate the axial bond, when you flip the bonds, carbon from one cyclohexane from one chair conformation to other, the axial bonds gets converted into your equatorial bonds when you flip. Okay, see properly. Similarly, when you see your equatorial bonds, when you flip your one cyclohexane from one conformation to another, there is an change in conformation. So see at the red hydrogens which are axial and the blue hydrogens which are equatorial. So when you flip, this is individual, and when you flip, you consider both the things together. When you flip this conformation, when you flip from one chair conformation to other, you see the hydrogens which are red, which are actually in your first conformation, gets converted to hydrogens which are equatorial in the second conformation. So there is a change in conformation of your hydrogens which are axial. It gets converted into equatorial, and the equatorial gets converted into your axial. So this is what happens when there is a flipping between the two conformations of your chair conformation of your cyclohexane. So these are the probable things we have to remember when you study. So there is a flipping, axial gets converted to equatorial, equatorial gets converted into your axial. So cis, what do you mean cis? Both the groups should be on the, so regardless of the position axial and equatorial, if the two atoms are bound to the top position, it is cis. Alternatively, if the positions are on the opposite side, then it is said to be trans. If the two groups are on the same side, then it is said to be cis, and if it is on the opposite side, it is said to be trans. Now, conformation of monosubstituted cyclohexane. Since the equatorial position is the most stable, as I explained, it is preferred over the axial position when flipping. So when there is a change in conformation, they'll try to see that the substitutions are always at the equatorial positions. Whenever there is a change flipping in the conformation, then the substitution will always attain an equatorial position. Okay, always attain an equatorial position, because equatorial positions are said to be the most stable form. Okay, whenever the substitutions are on the equatorial, then only it will be the most stable form. So there are some types of interaction. 1,3 diaxial interaction. What is this 1,3? The interaction between the first and the third carbon. First, and if you draw the structure, you can see the first carbon. If you see in the particular this thing, there will be two interactions. But carbon will interact with the first and the fifth, and first and the third. These are called as dihedral axial interaction. That is your torsional interaction because of the eclipsed group. Okay, if you see that they are like two butane which are joined together, molecules which are joined together, so they will have some interaction that will give you an energy which is associated to your strain. So this is energy associated with this thing is 7.6, because each dihedral angle corresponds to 3.8. So there are two interaction. That's why there is a steric interference. This is known as steric interference hindrance. So this has to be overcome. Okay, so whenever you flip between two, there is extra energy, that is 1,3 diaxial interaction, that has to be countered, and that is equivalent to 7.6 kilocalories joules per mole. So these are some of the conformations. Okay, you have to remember. See the conformation compound. Cis 1,2 conformation is axial interaction. So these are will be the conformation, and they will exhibit as the enantiomers. When it is trans 1,2, that will be both will be axial. When you flip, it becomes equatorial. It is diastereomers. Okay, cis 1,3 both are axial. They become diastereomers. Trans. So this chart you have to recollect. This chart has to be recollected when you study. What happens when there is a cis 1,4 disubstitution? Then the conformation will be axial equatorial. When you flip, it becomes equatorial and axial, and they are identical. So they are achiral. Trans 1,4, AE and AE, they are diastereomer, but conformations are achiral. So this is the relation between their conformation and your chirality. So this is how we can show. In case of trans 1,2 methyl, the methyl groups are opposite. In case of cis, they are on the same side. Okay. So when these are the various forms, what happens when they flip? So what happens when they flip? Your equatorial gets converted into your axial. So these are the examples of one of the example. What is the relations between the two compounds? When there is A is your cis conformation, B is your trans. Okay, so and when you flip, what happens? So there is no plane of symmetry with respect to A, B and C. B and C are chiral and optically active. As a plane of symmetry with A, achiral A, and optically inactive. So these are the relations between the three compounds. 1,2 dimethyl cyclohexane, which you have to explain. So this completes your acyclic stereochemistry of a cyclic compound.